Two problems we're going to work with today are 11.43 and 11.45. Both of these involve heat of fusion and heat of vaporization and all the concepts necessary. When you're working with problems like this, you need to calculate every single step of the way as whatever the substance is transitioning. For example, if starts as a solid and needs to go to a liquid, you have to calculate how much heat is necessary for it to go from a solid to a liquid. You also need to calculate how much heat is necessary for the liquid at that point to actually truly melt. That's where the heat of fusion and heat of vaporization come in. Starting with 11.43, the question asked to us is for how many years drinking water has been cooled on hot climates by evaporating it from surfaces of canvas bags or porous clay pots? How many grams of water can be cooled from 35 to 20 degrees Celsius by evaporating 60 grams of water? So imagine, if you would, we have a certain amount of water that's stuck in a clay pot, and we surround it with 60 grams of water on the outside. The outside water is what's going to vaporize. The energy necessary to vaporize the outside water has to come from somewhere. It's going to come from the water that we want cooled. The question is, how much water could be cooled with the water that is going to be vaporized outside? We need a few pieces of information from this one. We need to know the heat of vaporization of water, which is how much heat is necessary to transition water from a liquid to a gas, and also the specific heat of water. And let's plan this. First, we're going to analyze the heat necessary to vaporize 60 grams of water, because we know that means that is how much heat is lost by the water that's being cooled. So here's our plan. Using the heat of vaporization, the enthalpy of vaporization, we're going to calculate the amount of heat in kilojoules necessary to vaporize 60 grams of water within that temperature range. We're also going to use the specific heat of water to calculate the mass of water that can be cooled 15 degrees Celsius, which is the range of the heat lost. So we have two steps to the problem. Let's take a look and see what this will ultimately look like. In problem number 43, we're going to solve by calculating the amount of energy necessary for evaporating the 60 grams of water that was given to us. This is the water that's going to ultimately cool the interior water. So we need to know the heat of vaporization. It was given to us, and it happens to be 2.4 kilojoules per gram. From here, I can calculate how much energy will be lost when we evaporate this much water. The assumption here is that the water is going to gain the heat. So 60 grams of water. Set up my dimensional analysis formula and cancel grams, convert to kilojoules. Using the heat of vaporization, which is 2.4 kilojoules per gram, I can calculate the amount of heat gained by this 60 grams of water, which I can then assume is the amount of heat lost or will eventually be lost by the water I wish to cool. 144 kilojoules. I'm going to go ahead and convert this to joules right now, because I do know that specific heat of water is specifically listed in joules. Using scientific notation, because this is quite a large number, I end up with 1.44 times 10 to the fifth joules of energy that the 60 grams of water is going to absorb itself, and thus this is the energy lost by the liquid water inside. So let's cool that liquid water inside. Cooling a certain amount of water by 15 degrees Celsius. This is what the problem gave us over here. By the designation of amount, we're going to assume a gram of water that will be cooled 15 degrees Celsius. All right. We already know how much energy is going to be lost by the water. That was calculated by the first problem. We're going to lose 1.44 times 10 to the fifth joules of energy in the water we wish to cool. Using the specific heat this time. Remember, the specific heat of water is actually 4.18 joule per gram degree Kelvin. That's what was given to us in the problem. So here we're going to need and ultimately lose 4.18 joules of heat for every gram. I need grams in my final answer here. Knowing that, I can gradually take the joules given to me and work my way toward grams. I need to cancel joules first. I see that joule is on the bottom, so I invert the specific heat. Joules converted into gram per Kelvin, 4.18 to 1. This cancels joules. My next step is to get rid of the Kelvin, because I only want grams as my final answer. So I go ahead and cancel Kelvin, and we know that a 15 degrees Celsius change is the same thing as 15 degrees Kelvin. So I can go ahead and put the temperature change right there, 15. Once I solve, I end up with around 2,294 grams of water. Remember, we want grams as a specific amount available. So 2,294 grams of water can be cooled by the amount of heat evaporated by 60 grams of water. In the second problem I'm going to work with you today, 11.45, this one involves more steps, but it's similar to 43 overall. But we do have a large range of temperature changes and phase changes we have to account for. There's an enormous amount of information in this problem, so we need to write it down and look at it very carefully before we go ahead and try to work out the problem. Don't be intimidated by a problem that has this many numbers. It's just a large amount of phase changes that are happening. The solid phase, the melting portion, the liquid phase, the vaporization portion, they all have their own individual numbers, which is why we see so much. So in 45, ethanol melts at negative 114 degrees Celsius and boils at 78 degrees Celsius. The enthalpy of fusion, the heat of fusion of ethanol, is 5.02 kilojoules per mole. This is the transition energy necessary for a solid to a liquid or vice versa, a liquid to a solid. The enthalpy of vaporization, the heat of vaporization, is 38.56 kilojoules per mole. This is the energy change when it needs to vaporize, to actually transition from a liquid to a gas, or the reverse, a gas to a liquid. In addition to this information, we also need to know the specific heats of the solid and liquid ethanol, and they are 0.97 and 2.3 joules per gram Kelvin respectively. The specific heats are necessary when the solid is heating up or when the liquid is heating up, but not during the transition of a phase. Our first question is, how much heat is required to convert 42 grams of ethanol at 35 degrees Celsius to the vapor phase at 78 degrees Celsius? And then we're going to be asked how much heat is required to convert the same amount of ethanol at negative 155 degrees Celsius to the vapor phase at 78 degrees Celsius. Both of these will involve several phase changes. I should take a look at all those individual data points that are given to me and write them down first. So let's organize all this physical data and help me make sense of it. I know the melting point of ethanol is negative 114 degrees Celsius. At this point, I should be concerned with things like the heat of fusion. The boiling point is 78 degrees Celsius, and once again, once I reach that, I should be worried about the heat of vaporization. Speaking of which, I also wrote down the heat of fusion and the heat of vaporization, gathering the data from the problem, and the specific heat. The specific heat commonly uses a capital C, so the specific heat for a solid is 0.97 joules per gram Kelvin, and the specific heat of a liquid is 2.3 joules per gram Kelvin. These are useful when we're gradually heating up the solid or heating up the liquid before they reach their actual phase change. In the next problem we're working with over here, we have to calculate the energy necessary to convert the liquid ethanol from where it starts to all the way where it ends. The ethanol itself is beginning at 35 degrees Celsius and transitioning all the way over to 78 degrees Celsius. That involves a fair number of temperature changes, not just heating of the liquid, but also vaporizing the liquid. Let's focus on one step at a time. First, we're going to focus on heating the liquid. That temperature change is 43 degrees Celsius, which is 43 degrees Kelvin. Because we're heating a liquid, we're not actually undergoing a phase change. We're going to end up using the specific heat of the liquid. That was given to us as 2.3 joules per gram degree Kelvin. Now I can work on the stoichiometry, the dimensional analysis, and converting to the kilojoules necessary. Starting with this, I have 42 grams of ethanol given to me. I set up my dimensional analysis box. I'm going to abbreviate ethanol as ETHOH. Knowing I have to go to kilojoules and only having the specific heat, I try to cancel grams first. I see gram per Kelvin on the bottom, so I can go ahead and put gram per Kelvin on the bottom with joule on top. It's 2.3 joules per gram Kelvin. This ultimately cancels my grams. My next step is to cancel the Kelvin. I need to get rid of this because my final answer should only have energy. The temperature change was 43 degrees Kelvin. Cancel them out, and I'm left with joules. I do want to go to kilojoules in this problem. Number one, that's what I'm going to be adding up for the heat of vaporization in the future. Plus, kilojoules tends to be a better unit when we're discussing heat overall, unless we really need to use joules. The conversion factor is 1 kilojoule for 1,000 joules. Once I solve this problem, I end up with a heat change, a heat necessary of 4.1538 kilojoules of energy to heat this liquid to its boiling point of 78 degrees Celsius. This, however, is not the total amount of energy. Once it reaches the boiling point, it also needs to transition into the gaseous phase, and that's what I'm going to work on next. I'm going to vaporize the liquid at 78 degrees Celsius. Because this is a phase change, I will need to know the heat of vaporization that was given to me. Turns out that the heat of vaporization here is 38.56 kilojoules per mole. This is different than just simply heating up a liquid. A phase change will always use the heat of vaporization or potentially the heat of fusion, depending on what phase change is happening. Now I can use the dimensional analysis. We start with the 42 grams of ethanol, ETHOH, that we were given, and I'm only again convert it to kilojoules. However, my conversion factor has moles, and I'm given grams. If I cancel grams and convert to moles, I've still done a simple molar conversion, where 1 mole is equal to the molar mass. The molar mass is 46.07 grams per mole. This cancels grams. Now I can convert the moles to kilojoules using my heat of vaporization. Kilojoule is on top, mole is on bottom. 1 mole to 38.56 kilojoules results in a canceling of moles and an energy change of 35.153 kilojoules of energy. This is the amount of energy just to make it turn into a gas once it's already reached the boiling point. Now I know the amount of energy necessary to heat the liquid to the boiling point and to make it boil. So the total energy here is going to be from 35 degrees Celsius to 78 degrees Celsius, but also the vaporization energy from a liquid plus the vaporization. The liquid change was 4.1538 kilojoules. The vaporization change was 35.153 kilojoules. This graph right here is just a demonstration of the entire change that this liquid went through to turn into a gas. Thus, the total energy is the sum of the two. I'm going to add in the change for a liquid to heat up, 4.1538, plus the change in energy necessary to make it vaporize, 35.153 kilojoules. Together, 39.307 kilojoules of energy was necessary to make this ethanol heat up to its boiling point and also vaporize. This is my final answer, the sum of both changes. In part B, we're given what is essentially solid ethanol, and we have to calculate the transition from solid all the way to gaseous ethanol. That includes not only the heating of the individual solid and liquids, but also the phase changes of melting and vaporizing. We've got 4 kilojoules to actually calculate through each change. So we'll go from a solid to the melting. Eventually, we go through the liquid transition as the liquid heats up. And finally, we hit the vaporizing transition and calculate the energy for vaporization. This is a fairly long problem with 4 individual steps, and we'll be using heats of formation and specific heat. We'll begin by heating the solid from negative 155 degrees Celsius to its melting point of negative 114 degrees Celsius. The change in temperature is 41 degrees Celsius, which is also 41 degrees Kelvin. Because this is just a heating of a solid and not a transition, we're going to use the specific heat of the solid that was given to us. For ethanol, it's 0.97 joules per gram degree Kelvin. From here, I'm going to convert to kilojoules. So I'll write down the amount of ethanol given to me, which is 42 grams of ETHOH, ethanol. I'm going to cancel the grams. The only location I have right now is the specific heat, which is joules per gram degree Kelvin. So gram degree Kelvin will end up on the bottom. And I'll convert into joules. The ratio is specific heat, 0.97 joule per gram degree Kelvin. This cancels grams. My next step is to get rid of the Kelvin. I know the temperature change is 41 degrees Kelvin. Plug in 41K. This cancels Kelvin, and I'm left with joules. From previous problems, I know I should go to kilojoules because that tends to be the final answer, and I'm going to end up adding all of my kilojoules for each step. I cancel joules, convert to kilojoules. We know that 1 kilojoule is 1,000 joules. Final answer for the heating of just a solid is 1.6703 kilojoules of energy, just to heat the solid to the melting point. Now we have to think about melting the solid. This itself takes its own energy. The process of melting will ultimately use the heat of fusion. So let's melt that solid at negative 114 degrees Celsius, its melting point. And of course, the heat of fusion, which is a process of a solid turning to a liquid, or the reverse, a liquid to a solid, is 5.02 kilojoules per mole given to me from the problem. Now that I have this information, I'm going to convert the ethanol, grams of ethanol, into kilojoules. 42 grams of ethanol, ETHOH, cancel grams, convert to moles. The reason for this is that my heat of fusion is given in moles. I know that 1 mole is a molar mass, which is 46.07 grams. This cancels grams. Now I can cancel moles and convert to kilojoules using the heat of fusion. Turns out that 5.02 kilojoules is equal to 1 mole. Solve for my problem, and you end up with 4.5765 kilojoules of energy necessary to melt this solid completely and make it a liquid at that point. Now we need to heat up the liquid. We've gone from solid to melting. Now we heat the liquid up to its boiling point, and then we'll calculate the vaporizing energy. My third step is to heat the liquid from its melting point of negative 114 degrees Celsius all the way up into its boiling point of 78 degrees Celsius. So we're going to go from negative 114 all the way over to 78 degrees Celsius. The temperature change here is 192 degrees Celsius, which is the same thing as saying 192 degrees Kelvin. Because this is a temperature change of a liquid, not a phase change, we're going to use the specific heat for the liquid. It is different than the specific heat of the solid of ethanol. It happens to be 2.3 joules per gram degree Kelvin. Once again, I start with the amount of ethanol present, 42 grams of ethanol. Set up my dimensional analysis box, 42 grams of ETHOH. Then I convert it into joules. I'm going to cancel gram per Kelvin to get rid of the grams, similar to an earlier problem. 2.3 joules is equal to gram or 1 gram over Kelvin. This cancels grams. My next step is to get rid of the Kelvin. We know the temperature change is 192 Kelvin. I'm left with joules, and I still need it in kilojoules to add up to all the other previous kilojoules. So I will cancel joules and convert to kilojoules. This ends up with 1 kilojoule equal to 1,000 joules. Solve the whole problem, and you end up with 18.5472 kilojoules of energy to heat this liquid all the way from its melting point to its boiling point. The third transition is the vaporization. At the the boiling point, it must actually undergo the process of vaporizing. We already calculated this. From part A, we calculated the heat of vaporization necessary for this 42 grams of ethanol. So I can go back to the previous work that I did. 42 grams of ethanol has a kilojoule value of 35.1535 kilojoules of energy. Thankfully, I didn't have to go and calculate this by hand because it's already been done for me. Thus, the total energy from the solid all the way up to its gaseous state is going to be the sum of the heating of the solid, the melting of the solid, the heating of the liquid, and the vaporization of the liquid. 1.6703 plus 4.5765 plus 18.5472 plus 35.153. The total sum here then is 59.9476 kilojoules of energy for the transition to happen, which is about equal to 60 kilojoules of energy overall.